Okay. So this is the circuit, and what I'm going to do is the usual spiel. Let's define any unknown voltages, give them names. We'll give currents, directions, and stuff like that. So I'm just going to go ahead and call this one VZ, since it makes sense given the other names. I'm going to call this IY. I'm going to call this IX. I'm going to call this, well, there's nothing after Z, so I'll call this VA. This will be IA. And the remaining currents, so I'm going to do something a little bit different here. I'm going to call this IZ, and I'm going to call this whole loop in here IA. No, that forget it. I don't want to make this more confusing than it has to be. Forget it. IZ, IA. And I don't think we have to define the other currents because they're across voltage sources, so we should be fine for right now. And then I'll also give the nodes names. So I'll just number them. We'll call this node 0, node 1, node 2, node 3, and then node 4, which, as you can see, extends across the whole top there, right? So how do we solve this? Oh, it's really easy. It's like 2 lines. Probably take me longer to draw than it will to write. But so I'm going to say let's write out the equations that we know. The reason why I put this little note with stick with the relevant ones is because this is a big circuit and there's really only a small part of it that we're concerned with. So, as we get into more advanced problems, you want to try to be a little bit more efficient when you can and not just write out a whole bunch of junk. So let's start off by writing out a couple equations, and then we'll go from there. Since we're trying to solve for a voltage, and this rule doesn't always apply, but sometimes you do need KCL to solve for voltages. But since we're trying to solve for a voltage, yes?
Are we getting the equations on the quiz?
You are. You're going to get a cheat sheet. I'm going to put that on the Dropbox, and I'll send out a link. But really, at this point, there's no equations. It's Telegin's theorem, KVL, KCL, Ohm's law. I mean, and that you've used it so many times, you probably have it memorized by now anyway. Later on, it'll be more important to have that stuff on there. Okay, so let's try doing. I'm going to try to do it the way that they did it in the. Okay, so here's the tricky thing. So the trick to this problem, I mean, there's longer ways to do. Yes.
About the current direction, you said that we can choose what direction it is, or it always goes in one direction.
You can choose it however you want.
So if we did them all the other way, would it be wrong?
It wouldn't be wrong, but if you do them all the other way, like let's say for example you defined something like that, then you got to make sure to throw the negative in there, right? Because if you don't obey the passive sign convention, that's important. If you don't obey the passive sign convention, then you got to throw the negatives in there. That's the only reason why we try to stick with that. It's just to make it a no-brainer when we do our V equals IR over and over again. It's all positive. Okay? So there's lots of loops that you can choose here, right? You could choose a loop that looked like this. Okay, you could choose a loop that looked like this. You could choose a loop that looked like this. You could choose, I mean, et cetera, et cetera. But we have an unknown that we're trying to define, and we know that KVL goes by the loop, so we just want to find the loop that includes our unknown and has as few other unknowns as possible, right? Because that'll give us one unknown, one equation, and we solve. All right, so what is the loop that they chose for solving for Vx? So they chose this loop here. Now you may ask, well, that's not really a loop, right? You just cut across a big chunk of open space. So that loop actually looks like this. However, because they tell us that it's a 12-volt differential between this node, between nodes 2 and 4, you can essentially, right, you know that that 12 volts is equal to Vy plus 6 volts, which means that you can imagine it as being replaced. So when you write your KVL, it actually looks like a loop like that. Does everybody understand what I'm saying there, right? That's not the actual loop, but it's when we do the simplification, because of the value that's given right there, it ends up looking like that's the loop that we're using. Yes?
And we can use like what you just said to find Vy.
Well, in this case, we're going to use define Vx, right? Because it's Vx is included in there. Okay, so that's the first one we're going to use. So let's write out loop number 1's KVL. And so that is going to be Vx minus 4 volts plus 6 volts minus 12 volts equals 0. Let me check those polarities. So we have Vx, so plus minus, minus plus, minus plus, that should be a negative again. So plus minus, minus plus, minus plus, minus plus. Okay, and then the other loop that we can use in a similar vein. Well, let me ask you that question. So what loop would you use to solve for Vy? Yeah.
Like the 12 volt, 6 volt Vy.
Mm-hmm. Yeah. So then we have another loop that looks like that. All right, and so that loop is going to be Vy minus 12 volts plus 6 volts equals 0. So let me just, so that's this loop, and that's this loop. All right, and that's it. So we have our, so we'll take our equations from above. And there's really not too much to solve here. It's all almost done, right? So 12 plus 6 is 18, plus 4, so 22. So one's 22 volts, and the other one's going to be 6. So Vx equals 22 volts, and Vy equals 6 volts. So, good question. This is, very much a type of problem you could see, and I think it's a good example of showing how there's like a brute force way of doing these problems. You could just throw out all the equations and write them, and then try to combine them together and use algebra. But if you're a little bit selective in the beginning and think about, okay, I want to maximize the knowns, minimize the unknowns, then it can save you a lot of time. And this problem could have easily required 5, 10 equations in order to solve if we would have just been haphazard with the way that we chose our loops. Any other homework questions? Yes.
Number 6.
Okay, so for this one, I think I can just explain it. I don't necessarily have to do it in the... Yeah, go for it.
Is that, the equation is V equals I squared R.
Mm-hmm.
I don't understand why it's 1 over G and instead of 1 over G.
So G is, and this, again, remember, for real circuits, one over G. That's a G, not a 6. This is resistance. This is admittance. So in this problem, all they've done is put it in terms of the admittance. I squared R is the same as I squared 1 over GX. Because they're giving you a GX value, or they're defining it in terms of GX, and so that's what you're solving for. So you could solve for this as R. You could put I squared R. You could go through and solve the whole thing in terms of R, and then in order to get your admittance, your conductance, that's GX, you would have to, I labeled this wrong here, hold on. This is not admittance. This is conductance. Okay? Then the rest of the problem is, I guess you just solve using I squared R. All right, so any other homework problems or questions? Yes.
Number 13 on homework 1.
Okay. All right, so for this one also I think I can just sort of explain. So the voltage across an element is given by this equation right here. The current entering the positive terminal of the element is given by this other equation. So essentially what they're telling us is, right, we have our V, we have our I, and they're very, yes?
It was number 13.
Oh, 13, apologize. 13. Okay. So the power absorbed by the box here is 2 to the E negative 2 watts, 2t watts. Calculate the amount of charge that enters the box between 0 and 4 seconds. So we know that power, so there's a couple relationships we know here. I'll write them down. Okay. And so those are the two main expressions that we have to use. We know power is equal to voltage times current. We also know the charge is equal to the integral over the period of time that we're concerned with, the integral of current. So they tell us that this is, sorry, not that. They tell us that this is equal to 2 to the E negative 2t watts. They also, you can see in the diagram, tell us that this is equal to 4 to the E negative t. All right? And so we can use that in order to give us a current. So current will be equal to P over V, which would be 1/2 e to the negative 2t over e to the negative t, which is the same as 1/2 e to the negative t. Is that right? Yeah, okay. And then we take this and we plug this in right here. But our period of time that we're concerned with is going to be, as they say, between 0.1 and 0.4 seconds. So we have to find the integral. Sorry, I'm going through it quickly, but I just some of these the answers do a good job of explaining, and those I'll refer, and then some of them it doesn't, and I'll write it out. But this one they do an okay job. I think they just the worst thing about the solutions is that they just don't give any instruction or any context. It's just like equation, 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 solution, which I think is what makes them difficult to understand sometimes. Is even if they just put slight notes of what they were doing, it would make it easier. So we're taking the integral from 0.1 to 0.4 of the current, which is 0.5 e to the negative t. And then the integral of e to the negative t is equal to negative e to the negative t, right? E to the x. The derivative or the integral of e to the x is e to the x. If we have e to the negative x, then we pull the negative out front. So what we end up with is simply defining negative 0.5 e to the negative t over the interval of 0.1 to 0.4. So we plug in the values of 0.4 and 0.1. And once you solve all that, you end up with 0.1173 coulombs. So perhaps, I think that for some people, maybe that first step of doing the I equals P over V, realizing that you can do that with instantaneous or time-varying equations in the same way that you could do it with scalar values, that might have been confusing a bit. But you can do that, most definitely. All right. This is great. I do not want people to hesitate to ask homework problems because more times than not, that's where people get tripped up in this class. Any other homework problems? Yes.
Number 35 from chapter 1.
Okay. Okay, so this one deals with dependent sources, which we're going to talk about today. I'm sorry, I don't know why the ordering of my lecture, you can't see it. I don't know why the ordering of my lecture got thrown off where dependent sources came so late. I don't know, maybe I missed something when I was talking in the first lecture. But this asks us, find IX in the network shown, shown below. So this one I think I gotta do. Erase all this. Okay. Let me just make sure I didn't do that one already in the other notes. 1 second. Oh, I did. All right, so I'm going to refer to that then. So one thing is if you go to the homework solutions, you'll see there's a document down here called supplementary solutions, and that has solutions to some of the harder homework problems. And so we've already gone over 135, but I can use this to... Can I make this bigger? Guess not. Okay. So this is the circuit. 135, and I apologize for it being a little bit hard to see. This is when I used to do it on the board. Find IX. We have a 36-volt source. We have 3 elements which are defined just as boxes. And the reason why they're defined that way is because it doesn't really matter for the purposes of the problem. It's just they give you the voltage across it. 12 volts across, 24 volts across, 28 volts across. They tell us that this current is called IX. They tell us that this current is 2 amps. They tell us that this current is 2 amps. Right off the bat, you know what IX is, right? IX is going to be 4 amps, right? KCL tells you that the current leaving the center node will be equal to the current entering the center node. Then what we have is this third element that has 28 volts across it. And then we have this dependent source. So this is what we're going to talk about today is dependent sources a little bit. But the dependent source is really not that complex. It's just the voltage here across these 2 terminals is going to be equal to whatever the current is. So if its IX is 4 amps, that means that the voltage across those terminals is 4 volts. Okay? And so did they really give us all that information, or did I add something else in? I mean, you don't even need to do anything to solve I. Well, their intention, let's put it this way, their intention was for you to use Telegon's theorem in order to solve. So let's do that. Let's solve it that way. And we already know what the right answer is going to be, which is going to be 4 amps. So if we write out Telegon's theorem, okay, we know here, for this element, it will be negative IX times 36, because the current IX flows from the negative to positive terminals. We'll have here 12 volts times IX. Here we'll have 2 times 24. Here we will have -2 times Ix. Does everybody, this is really the one I think that trips people up. Does everybody understand why that would be -2 times Ix? I can't, it sounds both of them. Yeah.
Because the IX on the left side is traveling the same direction.
So that is the thing that trips a lot of people up. That's not the reason. So let's look at the voltage and the current independently. What is the voltage across the terminals? It's 1 times Ix. Take that value, set it to the side. What is the current flowing through it? It's 2 amps. But it's flowing in the opposite direction of the passive sign convention, right? It's flowing from the negative to the positive terminal. So that's the reason why there's -2. Has nothing to do with the direction of this over here. When you're using dependent sources, or you have a problem with dependent sources, you take everything exactly at face value. This says 1 times Ix. Whatever Ix is there, you plug it in over there, and that's it. You don't take into account the direction. You don't take into account anything else. So this will be -2 times Ix. This will be 2 amps times 28 volts, which will be 56 watts. So anyway, from here you can collect all the Ix terms together. That will give you a positive 26 Ix equals 104 watts. And then you can solve for Ix. Not the best problem, but I think the real thing you want to focus on is this element right here and understanding how that correlates to -2 amps times Ix volts, and why that why that equals the voltage being consumed by the element. Okay? Anything else homework-wise? All right. So let me spend 1 second talking about what we did last time, a quick review, then we'll jump into that homework problem, number 132, 232, right? 232, and then we'll cycle back into some of the new material. So last time, what did we do? We essentially finished up an example. We talked about the double subscript notation, where it described the voltage between 2 points. So VAB is equal to VA minus VB. Pretty straightforward. Again, it's just knowing to expect that, and just being aware of how to use it when it comes up in a problem. The big thing that we talked about was the voltage divider. So the voltage divider is a pretty simple but very useful circuit that you're going to see a lot, especially in ENG212 lab. You're going to use voltage dividers a lot. So voltage divider, can anybody tell me what that does? The name is sort of self-explanatory. Yes. Divides voltage, right? Takes a voltage in and it brings it down to some value less than 100% of whatever it was. And the way that we determine the ratio between the input and the output is using this equation right here. V out is equal to Vin times R2 over R1 plus R2, where R1 and R2 are defined using those the schematic that's shown above. And we know that this is an under-constrained problem, and what that means is that there's lots of different solutions that can fulfill or fill the void there. If we wanted to get a 50% step down, we could use essentially any two values that are the same, right? 100 and 100, 200, 200, 1,000, 1,000, whatever. We talked about deriving the transfer function for the voltage divider, and in the video it was a little bit convoluted the way that I did it because I made a mistake here, unfortunately, when I was first writing out the expressions, but eventually we got it right. And so what we showed was that using equations that we already know how to define, KVL and Ohm's law, we can look at the circuit schematic, we can highlight the appropriate expressions, and then we can make substitutions and combine things together in order to determine what the transfer function is. Yes?
Is the voltage divider strictly limited into only splitting it into two parts, or can it be multiple?
Well, you can build something that's like a voltage divider that can split into multiple parts. The thing about that is that only one of the values will be referenced to ground. So some of the other values will be differential voltages, right? Because only the final, whatever the last resistor is before ground, will be referenced to ground.
So the voltage divider itself can be two.
Generally, the definition we're going to use is going to be 2. If it were more, I don't know if I would use the term voltage divider. At least not the textbook wouldn't use it that way. And just bring up the homework problem. And so we came up with the same expression. Lastly, we talked about what would happen if we added a load in there. And what we saw was, well, first off, the voltage divider without any load is essentially not a very useful circuit, right? You're going to want to attach a load at some point, or else you'll never be able to use, quote unquote, use that voltage. So when we attach a load, that's going to change the way that the voltage divider behaves, because the original expression that we derived had the assumption that RL was infinite, which was a no-load condition. And so when we try to take a look at what happens when we add the load, the easiest way to do that is to simply just redefine our R2 as R2 prime, right? Where R2 prime is the parallel combination of R2 and RL. And then I spend a second talking about series and parallel combinations of resistors. For a parallel combo, we use this expression here. And so what we see is that for the non-ideal or the loaded voltage divider, we end up with a different expression. So as you would expect, the load is going to have an effect on the way the voltage divider works. The more interesting takeaway is that the closer RL is to R2, or the lower RL is, the more of an effect it's going to have on the gain. So the best case scenario is for RL to be much, much higher than R2, ideally infinite. But we're going to use this assumption here that we can consider the voltage divider to be ideal, quote unquote ideal, if the RL is 2 orders of magnitude higher than R2. So if R2 is 50, RL would need to be 500, and then you can just go ahead and use the regular expression. In a problem, if you see that separation less than that, then that means that's a sign that you're going to have to consider the non-ideal operation. And then we did a little example here. Okay. So now let's take a look at problem 232. I'm going to bring that up on the other screen here. One thing you'll note is that I am constantly updating this the syllabus here. I changed some of the links to just parse out the individual parts. I think it was easier. So anyway, for homeworks and solutions, you go here. I'm adding the lecture videos. It's easy to find them on YouTube, but all right. So homework number 2. And the supplementary solutions, let's see if we haven't already done it. I don't think it's in here. $264, $143. Okay, so no, it's not in there. All right, 232. And just to reiterate, I hope everybody understands the situation with the homework. Right, again, we're going to be using the homework assignments and the homework solutions. Essentially, all the homework materials are the ones that are available in the Dropbox. So that's what you should be studying from. That's what you should be doing. That's what I'm going to be going over in class. Newer versions of the textbook, change the numbers around. This is not an area that is evolving. Circuits is circuits. So there's not any new material that's been discovered in the past 10 years, let's put it that way. So, 232. Find VO in the circuit in figure P232, which is here. So I think the main thing that probably threw you off is the diamond, right?
Yes, it's
Okay.
VX that leads me off, because I was confused as to how they went clearly through with IX.
Sure, yeah. So I'm going through the lecture in the order that I've always done it. I don't know why this year it seems like the dependent sources are coming a little bit late compared to the homework. We haven't talked about dependent sources yet. But what I'll do is I'll spend a second now talking about them, and then we'll go through this homework problem, and it'll come up again in a second in lectures, I'm assuming today. But regardless. Okay, so first things first, how does a dependent source work? What is a dependent source? A dependent source, try to make this bigger. A dependent source is, in many ways, the exact same thing as an independent source. Well, first off, independent source means that there's a number assigned to it. It's independent of anything else going on in the circuit, right? Dependent source is still a source, and what I mean by that is the voltage across it is fixed. It's not defined by any internal impedance or anything like that. But our value of the voltage here is going to be dependent on the value of Vx somewhere else in the circuit, okay? And then this voltage here is going to be 2 times whatever that current is. Don't get mixed up with the voltage being dependent on a voltage, the voltage being dependent on a current, the voltage being dependent on a power, the voltage being dependent on the weather outside, the voltage being dependent on anything. Regardless of whatever is inside of those, assume there's parentheses here, whatever is inside of those imaginary parentheses, you multiply them all together or add them all together, and that's the voltage across those 2 terminals. Okay, so this and this work exactly in the same way. So now, if we want to write out KVL for this circuit, what we're going to end up with is an expression where Vx is going to show up 2 times, okay? And we're going to end up with an expression where Ix is going to show up, well, once, but actually in the end is going to end up showing 2 times once we do the substitution for Ohm's law. So, while the pencil for my iPad charges, I'll just talk about this in this way. Okay, so if we write KVL, so it says to find V out. Like we talked about previously, there was one other, well, no, that was when I did my office hours. Anyway, okay. So let's write out KVL, assuming to define V out. So I'm going to use this loop right here. I'm going to start with this source, and I'm going to say that this source has positive polarity, okay? And so it's going to be, actually they're using the inside. Okay, so there's 2 different ways that you can define V out. You can define V out using the outer loop, right, where this is V out, or you can use the inner loop. Does everybody understand why there's 2 loops here? Right? Because there's 2 different ways of defining V out. Both are valid. V out will be equal to the sum of these 3 voltages together. It'll also be equal to the sum of these 2 voltages together, in the same way that all the voltages in the loop will sum to 0. So the voltages on the inside are relatively easy to handle. If we assume that 12 volts is the positive polarity, we'll have 12 plus Vx, right, because Vx has the same polarity as 12, minus V out. And that's what you have. Oh, no, sorry, it has the same polarity. It's plus minus. So all three of these will sum together to 0. So you get V out plus 12 plus Vx equals 0. You can move two of these values to the other side, which will give you V out equals minus Vx minus 12. And then what is done right here is that Vx, we can make a substitution there with Ohm's law, right? We know that Vx will be equal to 12. Is it 12 times Ix or 12 times negative Ix? So we're doing this one a little bit more quickly. We're not drawing everything out explicitly, and we haven't labeled everything. So this is a little bit of an example of, as we get onto more and more advanced problems, how we can do things a little bit more quickly. So which one is it? Say it again. Negative Ix. And the reason for that is because that the passive sign convention would tell us that if it were R times I, that current would be flowing from the positive to the negative terminal, which would be from right to left, right? Since this current is flowing from left to right, that means that if we did all the switching of the directions in our head, it'll be 12 times negative Ix. And so we make that substitution down here, and you see what we end up with is, okay, so you make the substitution here as Vx will be, where did V out go? So Vx is equal to negative 12 Ix. Okay, so that's Vx. Oh, no, all they're saying is Vx equals negative 12 Ix. I'm sorry. This is not a simplification of the equation above it. Okay, that's what I was getting confused by. All right, so this is one equation, and this is another equation. They're two separate equations, right? Okay, now if we write KVL around the outer loop, so essentially why do we have to do the outer loop? Because we don't have enough values in order to solve for V out already, okay? In order to solve for V out, we need another expression, and then we'll take the first two and try to substitute them in. Again, this goes back into the situation of a lot of these problems relying on algebra ultimately, right? You have to have enough expressions to be able to solve for the value that you're looking for, and you have to know how to manipulate those expressions appropriately. So now, this is probably the trickier KVL, because this is the one where we're going to involve the dependent sources. So let's do this in our head. We'll say it, and then we'll go ahead and see if it matches what we should see. Okay. So first, I'm going to assume that this polarity here is the positive one for going around the loop. So 2Ix, okay, that's the voltage. 2Ix. And then over here, I'm going to assign this a voltage. I'll call it, well, essentially, it's going to be Ix times 4 ohms, right? Because the passive sign convention would say that the polarity will be positive and negative. So it'll be 2Ix minus 4Ix minus V out minus Vx equals 0. Okay, let's see if that matches what they wrote. 2Ix. They do the substitution already? Oh, they went around the whole loop. Okay, 2Ix. And unfortunately, they did it out of order. So 2Ix plus 12, right, because 12 has the same polarity, plus Vx. So these are the three elements whose directions or the polarities agree with one another. Then you have over here the two where the polarities are opposite. You'll have Ix times 4, and you'll have Vx. So you see them on the other side. Vx and 4 times Ix. So does everybody understand? Yes?
So the Vx from the opposite side, the current's going through, it's going from positive to negative. Wouldn't it have like the same polarity, have like the same polarity as the Ix? So isn't it supposed to be a negative Vx?
So this is a good question. And this is where people can get a little bit muddled on what's happening in a dependent source. The relationship between the Ix on the left-hand side in the source and the actual Ix, and the relationship between the Vx in the source and the actual Vx in the circuit is just purely numerical. You don't have to think about it any more than that. You could even just replace it with another, it's just you take the value, copy, stamp it. Doesn't matter what the direction is going on in the circuit, doesn't matter what the value is in the circuit. Okay, all you're going to do is just take that symbol and reuse it in another spot. So, so the only thing that we look at when we draw when we write up the polarities here is the fact that this is positive polarity, positive polarity, positive polarity. 2Ix plus 12 plus Vx. The negative polarities will be this one because the passive sign convention says it'll be Ix times 4 and Vx. These Vx's, one is an observed value, one is a dependent source. Their polarities oppose one another, and you just take that at face value. Does that make sense?
Sort of.
It's it can be a little bit tricky in the beginning to get a handle on.
How come it's not negative Ix times 4? You just said that the current is opposite, it's flowing from left to right.
Well, no, that was because for this one, because of the direction that Vx was defined, it's in the other. It's going negative positive, right?
You're saying that this is going from positive to negative.
Over here, I'm going to go ahead, since the voltage polarity isn't already given to us, I'm going to go ahead and assume that it's positive, negative. So I'm intentionally not writing this one out because I think it's good for us every once in a while to go through something, not sort of in our head, but it's an example of how to do this in more up here. Yes? So for the second equation, it all depends. Yeah, it all depends on what loop you're trying to examine. So essentially, there's three main loops that we could look at right here. There's this loop, right? There's the bigger loop, and then you could. We don't use it in this problem, I don't think, but you could also consider this to be a loop. So the reason why we consider V out is because this equation right here, actually both these equations, one is just a restatement of the other, they consider this small loop right here. And when I say that it's this small loop, it's really considering the whole entire circuit. Because if I were to go down here and take a look at this equation, see, this equation and this equation are essentially the same. Because V out contains this, this, and this. This is all here, 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 and here is part of V out. It's V out is equal to this plus this plus this. So if you make that substitution, this equation right here will solve to this equation right here. Okay, so we have KVL around the loop. We've taken the dependent sources sort of at face value, more or less. And now let's see how we can make substitutions in order to simplify. So the first thing is, right, we have two unknowns here. We have Ix and we have Vx, right? We have two instances of Ix, that's fine, we can combine them. And we have two instances of Vx. We have to get rid of one. The easier one to get rid of is Vx, because we've already written out an expression that tells us how to define Vx in terms of Ix. So I'm going to take this here, plug him in there, and plug him in right there. And so, now why is it positive? Negative 12 Ix. Is that part of the reason you were asking? Or
Yeah, I'm so confused about
Yeah.
Since you're solving for IX, doesn't it just cancel out the VX?
Well, yeah, I see. You could just subtract it over to the other side. Yeah, that would be an easier way of solving it. I'm still trying, but they were obviously not doing it that way. They were trying to solve with this 12ix. I think what ended up happening was that, like you said, because they cancel out anyway, the Vx and the Vx, this is a mistake. They use negative when it should be positive. The values go away anyway. So what ended up happening was they got the correct answer even though they used positive 12ix instead of negative 12ix. You see what I'm saying? If this were positive and positive, or this were negative and negative, as she just pointed out, they still go away, which actually we should have noticed up here that they would go away regardless. Anyway, this should be negative 12ix substituted in down here.
Well, I understand why they made that positive because there's a negative out in front because the VO polarity is different. It goes from positive to negative.
No, it shouldn't, because this is, you just do a straight up substitution. This is plus Vx. This is plus Vx right here. So this value should just be taken and plugged in directly right there. Yeah,
Can you explain why it's negative?
sure. So if you go up here to Vx, you see that the voltage polarity is positive negative. That means that the passive sign convention would tell us that the current flows from right to left. So the V equals IR would tell us that, so V equals 12 ohms times the current flowing in the other direction. Hence, we take negative Ix. So Vx equals 12 times negative Ix. Anyway, so this is a mistake that ends up working out anyway. What I'll try to do is I'll make a note to myself to correct this in the solutions. I'll just take a picture of it. Okay. So I'll correct it, but anyway, to make a long story short, right, that should be negative 12Ix. It goes away anyway. You end up combining terms together. So you have 2Ix, or 4Ix minus 2Ix. That leaves you with 2Ix equals 12. You divide by 2, Ix gives you 6 amps. And then you have this value. You can substitute it back into the equation above to give you Vx. So Vx will be equal to negative 12 times 6 amps, which gives you negative 72 volts. And then we can plug that in here in order to give us our V out, which is V out is equal to negative 1 times negative 72 volts minus 12, and V out gives you 60. So the problem's right. And actually, you could make an argument that this line is right if they took the Vx's and switched the sides, which would be a completely nonsensical way to do things. But anyway, the real reason is that they have graduate students doing the homework solutions, and as long as it comes up with the right solution, no one's checking to see if it is actually right. So the main takeaway, the main takeaway from this problem is how to treat the dependent sources and not to start overthinking them in a way where you're trying to account for the polarity of, if you have Vx and a Vx is a dependent source and Vx somewhere else, to not be trying to line them up or make their polarities match. It's strictly a mathematical relationship. It doesn't matter at all. You just write it exactly how it is on the schematic. And so I'll spend a second at the beginning once we get into the new material talking about dependent sources. But does that make sense as far as the homework problem is concerned? A lot of these problems you just got to be really good at defining your KVL and your KCL, and you'll be in pretty good shape. So are there any other homework problems? Actually, before I move on, let's talk about the quiz in more detail. So first things first, the quiz will go up until the lecture notes from Friday. Okay, the lecture number 3, that's the one that is just handwritten. Okay, so you should be studying material up until that point. And then as far as the homework is concerned, in my mind, we haven't touched upon dependent sources yet, okay, in the lecture. So I'm going to draw the line with regard to the homework at right before this 232. So this 232 would fall into the next quiz, whenever that is going to be. Okay? So the homework problems up until 228. So that gives you a very concise area where you got to study. All of chapter 1 stuff, chapter 2 up until the lecture number 3, and all the problems, including chapter 1, up until 228. That's what you should expect to see. Yes?
Not including 228.
No, including 228. Sorry. Maybe I should say stopping at 228, not including the one we just went over, which is 232. And that's good because that'll give everybody a couple more days to digest the 232 thing, and it'll give me a chance to fix it in the PDF. So I'm just trying to find where we left off last time. Okay. So, as I had said, the first thing that I have in my notes to go over this time is a dependent source. So what is a dependent source? I won't spend or go into that much detail because we did just spend 5 or 6 minutes talking about it. Okay, so the simplest way to look at it is imagining them in separate circuits. If you imagine them in separate circuits, it sort of takes away all the confusion of, trying to line up the polarities and stuff like that. So let's take a circuit or 2 circuits that look like this. Okay. So dependent source, shown here, all you do, again, like we said before, you just take the value. This voltage is equal to 3 times V1. Our V1 is defined right here. In order to solve the circuit on the right, we got to solve the circuit on the left, get our value of V1, and then we'll have our value of V2. Okay? Dependent source, all it means, a source that's dependent on another value. It doesn't matter. If there's a plus and minus inside of it, it's a voltage source. Regardless of whether it's dependent on a voltage, dependent on a current, dependent on a power, dependent on the weather outside. If there's an arrow inside of it, which we haven't talked about current sources explicitly, but we will. If there's an arrow inside of it, that means it's a dependent current source, which means it's defining a current, okay? Regardless of whether it's dependent on a voltage, dependent on a current, blah, 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 blah. So you can have voltage-dependent voltage sources. This would be an example of that. You can have current-dependent voltage sources. A current-dependent voltage source would be if that looked like that. It's still a voltage source, but it's dependent on a current. And then you can have the other combination, which would be voltage-dependent current sources and current-dependent current sources. So let's solve this and figure out what the output V2 will be. It's a very simple circuit. First things first, what is V1? It's simply equal to 5 volts. Right? This is the voltage V1 is in parallel with the 5 volt input. That means that this source is 3 times V1 is equal to 15 volts. So we're going to consider that to be a 15 volt source. And so when we solve, V2 is equal to 15 volts minus what our current is times a 0 resistance, which is just going to be the same, so equals 15 volts. So a very easy circuit to solve, but the main point there was to illustrate how the dependent source works. So there are 4 different types, like we just said. There is the source type and the input type, 2 different things that we have to worry about. So we have the source or the output type, meaning what does it generate. And then we have the input type. In other words, what is it dependent on? So we have the voltage source, and we have the current source, sorry, it's not lining up completely. And then as far as inputs, we'll also have voltage, and we'll have current. Okay, so what are these going to be called? This is what we call a voltage controlled voltage source, VCVS. This is what we call a voltage-controlled current source. So the last two letters describe what type of source it is. The first two letters tell you what's controlling it. Down here we'll have the other combo. We have a current-controlled voltage source, and then lastly we have a current-controlled current source. Okay, so what do those look like? Both the dependent voltage sources look the same. Diamond with a plus and minus on the inside. Okay? The only difference is whether it's dependent on a voltage value or a current value. Both the dependent current sources also look the same. Diamond with a little arrow inside. The only difference is whether they're dependent on a voltage or a current source. You could have something crazy like this. That wouldn't fall into either one of the categories. That's not really something that is used physically. It's not really physically realizable. And what I mean by that is like a voltage-controlled voltage source represents an amplifier a lot of times. Current-controlled current source represents a current mirror. Okay, there's different devices that actually mimic this type of behavior. When you add two different inputs, I mean, it might be something you could see in a homework problem. Why is this not working? But it's not. For all our intents, we're going to ignore that situation. Okay, so those are the four different types of sources that we have. Voltage, VCVS, VCCS, CCVS, CCCS. And again, the output is going to be a voltage. The output is going to be a current. I'll say I. The output is going to be a voltage, and the output is going to be a current. Now, one thing that we haven't talked about current sources too much. I think I mentioned it in passing.
Go back a little bit.
Yeah, sure. I'll leave that up there for a second. So current sources, I mentioned in passing, I know it's come up in some of the homework problems, and maybe there's a little bit of background, more background that I can give there to help. Current source, just like a voltage source. And let's ignore the whole idea of dependence for right now. Let's just say good old independent current source. How do you use that? Okay, I'm not even going to draw the whole circuit. I'm just going to give you one juncture of a circuit. I'm going to say that this is I don't really need to label that much. I'm going to call this node X. I'm going to call this current I3. I'm going to call this current I2. And I'm going to call this, I'm going to give this a value of I1. So just like the way that an independent voltage source tells you what the voltage is across two nodes, a current source tells you what the current is flowing along a branch. Doesn't matter what else is happening along that branch. The current flowing along it is equal to that I1. So how would we treat this? If we were to write out KCL, what would KCL look like? We would have I1 is equal to I2 plus I3, right? The current coming into the node is equal to the two currents leaving it. Furthermore, if I were to try to calculate the voltage, across this resistor right here, it would be equal to negative I1 times R1. Because we already know what the current is flowing in that direction. The resistor is in series with the current source, and so that current is I1. Why is it negative? Again, because it's going against the passive sign convention. To obey the passive sign convention, we need a current flowing like this. And so the value of this is negative I1. So is the idea of current sources or that concept something that I need to talk about a little bit more? Does it kind of make sense? It does? Okay, good. So because you've already seen some current sources coming up in your homework problems, that is something that's going to be fair game for the test. Okay. Even though it's coming in this lecture, you've already had it in the homework problems in 120 or 228 and before. So I'm going to consider that fair game. Yeah, a question?
I mean, the quiz?
Quiz, test, same thing. When I mean midterm, I'll call it a midterm. Or a final exam, I'll call it a final exam. All right, so let's take a look at a network where we have multiple sources and resistors. And we've already seen that, okay? Our homework problems, right, many of them have had multiple sources, multiple resistors. But there's some tricks that we can use in order to simplify. And that's going to help us later on. So let's take a look at a circuit that looks like this. Okay, so V1, V2, V1, V2, V3, V4, V5, R1, R2. All right. Now let's use passive sign convention to set up what the voltages and the currents, so the voltage across and the current through the resistors would be. So I'm going to call this VR2, give it a direction like this. I'm going to call this VR1 and give it a direction like this. And in order to make everybody happy, according to the passive sign convention, I can just use one current, which is going to be called I. That satisfies passive sign convention for both of the resistors. So let's say I asked you Let's say I asked you to solve this, okay? You could write out KVL and Ohm's law to solve. That would be similar to the way that we've done it in the homework. But there's, and when I'm solve this, when I say solve this, I'm going to say solve for I. So you can write out KVL, Ohm's law, and you could solve it that way. We know how to do that. But what if there was an easier way? So what if we could simplify the circuit and then solve it? So what we're going to do is we're going to solve this the old-fashioned way, and then we're going to show that there was a simpler way or a simplified way that we could have solved it from the beginning. Now I know this class is repetitive, okay, and it's intentionally repetitive. This material, these writing KVLs, KCLs, like over and over. Somebody save me, I can't take it anymore, right? But this stuff, it needs to become like second nature, because once you get to electronics, once you get to later courses, you're going to be, the first 30 seconds of the problem is going to be doing this. And then you're going to need the rest of the 25 minutes or whatever in order to get to the real bulk of the material that we're working on. So my goal is not only just to give you an understanding of circuits, but this should become like second nature. Okay, not that every class isn't important, but this one is especially important for moving on to the later courses. So let's write out KVL. And I'm just going to go around from starting from V1. So we have V1 minus VR1 minus V2, right? Just really quickly eyeballing the polarities, plus V3 minus VR2 minus V4 plus V5 equals 0. Let me check that. So, right, minus, minus, plus, minus, minus, plus. Okay, and what I can do, I'm going to separate the voltage sources from the elements that are associated with the resistors. And so what we'll end up with is something that looks like this. V1 minus V2 plus V3 minus V4 plus V5. And then I'll have plus minus VR1 minus VR2 equals 0. Right? Next, I'll make my substitution. For Ohm's law, which is essentially going to tell us right here that this is equal to IR2, and then the other one's going to be IR1. So what we have is V1 minus V2 plus V3 minus V4 plus V5. And then we have, I can pull out the I, and I can also pull out the minus. Now what if I rename these? Then what we'll see is this equation here describes a circuit that looks like this. With the same current flowing through it. And so, what does this tell us? So what does this tell us? It says, so for single loop circuits, like the one that's shown up here, we can solve it in an easier way. We can take all the voltage sources, we can group them together, we can sum them up, make it a single source. We can take all the resistors, we can group them together, sum it up, make it a single resistor. And then, for the current through that loop, we can solve in a much simpler way. Single voltage source, single resistor, VI will equal V over REQ, right? The problem is that you will lose resolution, meaning that some of the values, as you simplify, are going to go away. And this is going to be something that we're going to see multiple times throughout this class. A lot of times we'll have strategies for solving circuits that are going to require us to simplify, pull values out of the circuit. When you lose resolution, and there's a value that the problem asks you for, so let's say, for example, this problem asks you to calculate I as well as VR1. You can use the simplified circuit to give you I, and then all you have to do to get your VR1 back is just plug it in to Ohm's law right here. Right? VR1 is equal to I times R1, and you'll have your value back. So that's how we can use combinations of resistors and sources in order to solve. Now, note that I said that that works for single loop circuits. So let's say you have a circuit that looks like this. Okay, for this one, it's not a single loop anymore. So you can't just sum all these voltages together and sum all the resistors together and solve for the value. Yeah.
If you had two resistors in the same loop, would you then combine those together?
Well, yes, because that would fall under our definition of series resistors, which we talked about last time. So yeah, so if you have, let's say, let me redraw this a little bit. Okay, so you can combine these two. And you can combine these two. But not for the whole thing. And especially, you can't combine this one right here. That cannot be combined with the other two. They need to be part of the same single loop. And so over here, right, there's only one loop that addresses these two sources. They're in series with one another. They can be combined. These two resistors, the same thing. Over here, you can't do that. Okay. So I'm going to go ahead and stop there because the next example gets a little bit complicated and there's only 4 minutes left. So there's really no way to start it. Main thing, remember, we have our quiz next time. It's going to be at the end of class. Okay, last half.